Hi, my name is Dr. Joe Sylve, and I'm the Director of Research and Development at BlackBag Technologies. Today we're going to discuss revisiting the linear hash. I'd like to start by saying that this presentation is not yet a formal proposal, and it's likely going to change and will be a subject of a future paper. At this point, I'm actively seeking comments from any and all interested parties who would like to work on this with me, and I'm not yet encouraging tool vendors to put this approach into their tools. If you'd like to work on this with me, please contact me either via email at joe@blackbagtech.com or via Twitter at jtsylve. Everyone here should be familiar with cryptographic hashing. Cryptographic hashing of evidence has been common practice since the beginning of digital forensics discipline. It's absolutely essential to what we do. It serves multiple purposes. First of all, integrity. We obviously want to make sure that during the course of our investigation, we're not modifying the evidence itself. So we can do this by hashing the evidence files before we do our investigation and after. And if that hash has not changed, then we know that we haven't changed the evidence. Identification. Often in our digital forensic reports, we are identifying evidence images based on their cryptographic hash. So by calculating the cryptographic hash, again, on a specific image, we can determine that that image is the exact image that is being talked about in a given report. And sometimes we also use cryptographic hashing for attribution. We might hash an original evidence source, again, a hard drive, what have you, to make sure that it still matches the hash of the image. That way we know that we have a bit-by-bit copy of the evidence. Now this isn't always possible these days due to TREM and other factors, but it can still be useful. By far the most common approach of hashing is going to be your linear hash. And when you think about cryptographic hashing, this is probably what you're thinking. With linear hashes, what we do is we read every single bit of data in order and apply it to a hashing algorithm of our choice. A single flipped or misplaced bit of data should result in a drastically different hash value. To verify the hash, we just repeat this process. We go ahead and we image every single bit in order from the beginning to the end. While our hashing methodologies may not have changed much since the beginning of our discipline, modern evidence sure has. Many of our modern evidence types have areas of unmapped or unreadable data. Consider virtual memory. Each process on an x86 processor, for example, has a large amount of virtual memory allocated to it, and most of that memory is unmapped and unreadable. APFS fusion containers are also a good example. APFS fusion containers actually map blocks from multiple different hard drives, and there's a large exabyte scale gap in between these two drives. So it's not really possible to linearly image or linearly hash this in any sort of reasonable time. We also have a lot of sparsely allocated drives and files to deal with. Why are we going ahead and imaging drives that are mostly unallocated, mostly contain null data, and spending our time hashing and imaging this stuff when we can really just be storing only the data that actually matters? Modern imaging formats like AFF4 know this and support sparse and out-of-order logical images by mapping data across multiple data streams. This allows you to image only the useful data in one stream in whatever order you choose, and then reorder and fill in the gaps when reading linearly from another data stream. With our modern evidence types, we run into a lot of problems with linear hashing. First of all, linear hashing is just that. It's linear. It's serial by nature. We're limited by a single core performance of our CPU because we cannot parallelize this process. We have to read the bits in order every time. While single core speeds have plateaued, our evidence sizes and our I/O speeds have increased over time, so we've got a lot of wasted opportunities here for parallelization. It also doesn't handle sparse data well. We have to feed the algorithm with something for the sparse data, and usually we have to agree on what that something is. So for the areas of unmapped data, most of the time we're feeding tons of blocks of zeros. So why are we wasting our time just imaging tons and tons of zeros when we could just be skipping over that data and doing only imaging the data that actually matters? It's also difficult to inline hash sparse and out of order data. And by inline hashing, I mean we can actually hash data as we're imaging the device, right? So you read a block of data into memory, you hash it, you feed that data into an algorithm, and then you push that data down to your image file. And you repeat this process. And by the time we're finished imaging, we already have a cryptographic hash, and we just need to hash the data one more time to verify that these two hashes match. Well, when you're dealing with sparse and out of order data, that produced hash is not going to match the linear hash that you get when you're doing your validation process at the end of the process. There are other approaches used to handle sparse and out of order data. First, we could try to hash the logical imaging stream, including the sparse zeros, after we finish imaging and again during validation. This is what we call a linear hash. This is what you're familiar with. We could also hash the image file itself, and by that I mean the AFF4 file, for example. This allows you to hash the smallest amount of data. However, we have a reproducibility problem here. If you image the same evidence source twice with two different AFF4 files, even if the logical data hasn't changed, that image hash is going to change just because the metadata that's embedded inside our image format is changing over time. Hash just the logical data that you're adding to the image and then in the order that's being imaged. And this is my preferred approach. I call this a data hash, where basically it doesn't matter about the zeros. We don't care about that. We don't care about the actual order the data is being added in the image. We just hash the actual data we're putting in the image and the order that we're putting in the image. And if we want to guarantee integrity and all that stuff that we need, we just hash that same data again. So we're only hashing the actual usable, readable data. And then again, you have your other stream that you can map and reorder this data and read out sparse stuff. This is obviously not going to match the linear hash if you try to hash that. So your image format needs to have a way of letting you know that we're using a data hash here and not a linear hash. Otherwise, your hashes won't match. There's also an approach called Merkle Hashes, and this is a way to parallelize hashing. And the idea here is we can speed up hashing by hashing individual blocks of data in parallel, and then storing those hashes for each of those blocks, and then ordering those hashes and hashing them in a tree-like format to produce one single hash. So we're hashing the initial data, and then we have those sets of hashes, and then we're taking hashes of those hashes in a tree until we get the final hash value. And this final hash value is going to change depending on obviously which cryptographic hashing algorithm we use. A SHA-1 hash is not going to match an MD5 hash, but also the chosen block size. So if you chose your block size at 4K blocks, you're going to get a different end resulting hash than if you chose 4 meg blocks. And that's even if the data is exactly the same. So when you're validating Merkle hashes, you need to make sure you're not only using the same algorithm, but the same block size. So what am I proposing here? I'm not saying that there's something better than linear hash. There's not one thing. There's no one-size-fits-all hashing solution. But as we start to use some of these non-linear hashing options, our tools and evidence imaging formats need to be able to better communicate our hashing choices to the investigator. If investigators are ever going to understand this, and they're going to want to know, I'm used to just seeing SHA-256 and some bytes. I know what that is. Now if I'm seeing something else, we probably all need to be showing the users the same thing. We need to adopt a standardized way of communicating this information in our tools, rather than just showing the cryptographic algorithm and the hash values alone, and then the investigator has to guess, is this a linear hash, is this a data hash, is this an image hash? So what could this look like? Basically, rather than just showing an algorithm and a hash, we would show some sort of indicator. Some of these parts here are going to be optional, and some of them will not. In the red here, and I apologize for those of you who may be colorblind, but on the farthest left block, we have our Merkle indicator, and this would only actually be shown in a tool if you used a Merkle tree implementation for hashing. So you'd have an M and then a dash, presumably, and then you'd have to put the block size. And that block size could be 4K, it could be 4 meg, it could be whatever. That allows the user to know, and the tools to know, that a Merkle tree hashing scheme was used, and we know exactly what the block size is. That way, if we want to validate the hashes, we can go ahead and validate them with those parameters known. The green, or the center notion here, is going to be the cryptographic algorithm used, and this is always going to be required. And this is what you're used to. This is MD5, SHA-256, what have you. And then on the far right, or in the blue, we have our hashing approach. And I say that this is optional. It's only optional, really, if you're using a linear hash. If you don't provide this at all, we're assuming that you're dealing with a traditional linear hash. But if this hash is not of the logical linear data, we go ahead and we can put either an I to say that this is a hash of the image itself, the AFF4 including all of its metadata, or a D, which is saying that this is actually based off of the data stream that's just stored in the imaging format. So some examples of here. So on the first, this is exactly what you see in your tools here, and this approach is sort of backwards compatible, because you could just say SHA-256, and from that we know that this is a linear hash of the logical data in the image, and uses the SHA-256 algorithm. This is exactly the same as if you would use SHA-256-L, because the L just explicitly says that this is the linear hash. Using the same approach in -I, now we have a different hash value because this isn't the hash of the logical stream of data that's in our AFF4 file, for example, but the hash of the AFF4 file itself. And similarly, if we want to use the -D, the D says that this is a data stream. This is the hash of only the data that we added to the image in the order that we added to the image. So it should be very quick because we're not having to bother imaging zeros to indicate sparse data or what have you. And if you used a Merkle hashing approach, you could do what you see here in our last example, where we have the M that says we use a Merkle hash. And in this example here, we use 1M, so that's a 1 megabit block of data. And then we have our SHA-256 algorithm. And again, you could always have a -I or a -D if you were Merkle hashing the image file itself or the data stream itself. In addition to our tools communicating to our users what hashing schemes were used, our image formats need to be able to communicate to our tools as well. So for analysis tools to know which methods were used, it will also be important to extend our imaging formats to support this additional knowledge. In the AFF4 format, it currently only supports an AFF4 hash property that really implies a linear hash value on a stream. There's no standardized way of saying that this is a data hash. And obviously we can't be storing image hashes inside of images because we're hashing the image itself. So by adding the hash to the image, that would change the hash value of the image. So we really only need a way of communicating linear hashes, which we already have, and data hashes, which we don't have a standardized way to do. In Macquisition, we actually employ data hashes when you're imaging APFS devices. Because like I said, APFS fusion devices have a large exabyte scale gap in the middle, and we can't really be hashing all those zeros. We do this by indicating on the logical image stream that you're reading from, we indicate a property called the integrity stream property. And that points to another object. That points to the data stream that we're actually imaging to do the integrity hashing. Maybe something like this could be standardized in the AFF4 format. And in addition, we need to extend the AFF format to considering adopting values for Merkle hash. So rather, as an alternative to the AFF4 hash, which implies a linear hash, and the integrity stream, which implies a linear hash from another data stream itself, we need the Merkle hash options. And the Merkle hash will also have something like a Merkle hash block size property as an alternative to the AFF4 hash property. And this will obviously only be used if Merkle hashing schemes are used to parallelize hashing. So we'll now open up for any sort of questions or comments. If you can reach out to me either directly or via email at joe@blackbagtech.com or on Twitter at jtsylve. Thank you very much.